Okay, thanks. Thank you all very much. Really appreciate the invitation and to come here and give a talk. There may not be many non-self-adjoint operators appearing in this talk, but I hope at least I can interest you in a new direction of research that I've been looking at with some collaborators in Vienna, a new postdoc of mine in Cambridge, and a collaborator in Australia. And so the setting is slightly different, and I appreciate the audience here is maybe not as well versed in cosmology, so let me set the scene slightly. So the idea is we would like to understand the dynamics of matter in our early universe, and in particular we'd like to understand how matter clumps together. So just what I have here is our best understanding, let's say, kind of a snapshot of our best understanding of the evolution of our universe. And so just to remind you, if you haven't watched Big Bang Theory, is our universe started in a Big Bang. Our best understanding is very dense, highly dense kind of quark gluon soup, okay, which somehow expanded. There would be quantum effects, lots of different theories what might have happened. So this is what we call the quantum fluctuation period and inflation. So you should imagine that we've got different subatomic particles, things are kind of bouncing off, they've got so much energy, they can kind of interact with each other, we can have annihilations, photons can just annihilate and self-annihilate, things like this. But everything is expanding, okay? And as it expands, it starts to cool in temperature. And at some point, it cooled sufficiently that some of these subatomic particles start to come together, so like hydrogen forms. And that means that photons are free to escape. Okay, and so when the photons are free to escape, they transmit out, and they have what we call the cosmic microwave background. They have this afterglow light pattern. Okay, and so this, from my mathsy point of view, is going to be my initial data, let's say, my starting point. So after this imprint, okay, of our universe, we think about 380,000 years after the Big Bang, so very, very old, we then start to get the evolution of our universe. So you can imagine that we've got all this matter, we've got hydrogen have started to form, certain baryons are forming. But of course, when we look at our universe, we see galaxies, right? We see larger structures. And so these started to develop over the course of our universe. Okay, we get the developments of galaxies and planets. But then observations suggest that at about 5 billion years ago, the expansion of our universe changed quite dramatically, and we entered an epoch of what's called accelerated expansion. So Claude, in his talk, introduced lambda, a cosmological constant, actually which I've got on my slide here. He introduced this cosmological parameter lambda, and we put this into our equations because we basically don't understand why our universe now expands at an accelerated rate. Okay, we don't understand what matter, what force. There's obviously lots of different theories, but it's very hard. We don't yet have a kind of a truly agreed upon explanation for why 5 billion years ago our universe started to expand at this ever increasing rate, at this accelerated rate. Now, the rate of the expansion, how quickly our universe is expanding, is obviously something that pulls matter apart, but then gravity is attractive. Okay, and so there somehow has to be a competition between these two effects that is sufficient to lead to structures forming, okay, densities kind of getting concentrated and so on and so forth. Okay, so this is kind of the big snapshot, and let's say from the PDE point of view, what you might be interested in, let me just say that we have a very good PDE understanding of this latter epoch, okay, accelerated expansion, but the upshot seems to be that structures are not forming there. Okay, and what I'm interested in, what I hope to talk to you a little bit about today is this early epoch, okay, where we don't have as quick expansion, and we'd like to better understand how structures are forming, how densities are growing, and so on. So I'm interested in what we call cosmological solutions to the Einstein equations, but actually today I'm working in enough kind of simplicity that I don't need the full Einstein equations out there, but I've just put them here on the board, just here on the slide, just to remind you that these are the fundamental equations of Einstein's theory of general relativity, okay, which supersedes Newtonian gravity. And it's a theory where your fundamental object is not the gravitational potential now, but it's a space-time metric. So it's a metric G on what we call a space-time manifold M. It's space and time, so it has one time, and today it will have 3 space dimensions. And it has a split signature, minus, plus, plus, plus for me, okay, in order to be able to measure distances between points in space and time. Now what's fundamental in general relativity is that this space-time, this object is how the gravitational force manifests. Okay, so in particular, if we think of the Earth, okay, is a big massive object. Okay, the idea now in Einstein's theory is that this big massive object, okay, is going to warp the space-time around planet Earth. And so when we pop a GPS satellite up around planet Earth, it is moving on a geodesic in this warped space-time. Okay, so in particular, as it moves, as this GPS goes around planet Earth, it undergoes a special relativistic effect because it's moving really quickly, but it also undergoes a general relativistic effect, okay, because the force of gravity is weaker up there than down here. Okay, but it's moving in this warped space-time is maybe how I think of these things. And so on the left-hand side, we have, let's say, some measure of the warping of the curvature of this space-time measured by things like the Ricci tensor and its scalar. In cosmology, we also just need to add in something to the equations, okay, ad hoc, this lambda g term, which is going to be the cosmological constant. And then on the right-hand side, we have any matter that's contained in the space-time. So this could be things like a wave field, a Klein-Gordon field, Maxwell's equations. For me today, it's actually going to be an idealized fluid. Okay, it's going to be an idealized relativistic fluid. So I mentioned this relic blackbody, or this relic radiation, this imprint that we have. So this is a picture here of an observation of the cosmic microwave background. Okay, and it follows the Planck spectrum, okay, of a blackbody object. And let's say what's really important to understand is that you can look out this way from planet Earth and you can take a measure of this spectrum, and the spectrum is characterized by one temperature, T. Okay? And if you look out this way, it will have temperature T is 2.72548. And if you look out the other direction on planet Earth, it will have the same temperature. Okay? And what's quite incredible is that it is highly isotropic. Okay? So on this picture here, it's obviously Earth projected down. And you've got red spots and blue spots, and you might be like, well, this is showing the temperature gradient, and you might say it looks like they're quite different, right? Red to blue is quite different, but the variation here is of the order of a mu, which I presume is a micron or something, okay, 10 to the minus 6. Okay, so it's very small. Okay, so actually we're able to measure this temperature to a high degree of accuracy, and what's quite incredible is if we look in all these different directions, it gives us the same temperature. Okay, and so what this tells us is it tells us that in our very early universe, okay, at this point when this was emitted, we had an isotropic distribution of matter. And because we have isotropy on the right-hand side of the Einstein equations, that's going to force some isotropy on the left-hand side of the Einstein equations, and that's going to force some simplification in my space-time metric. The other thing to say is, okay, that's just isotropy. We also don't believe that planet Earth is in a special place, and that's going to give us homogeneity. Okay, that's going to be the other part. But before I go to the next slide, let me just say this last sentence here, just so you understand in cosmology kind of what people study. So even though the CMB is highly isotropic, it does have anisotropies. Okay, there is variation, as you see in this color map here. Now what the standard model of cosmology does is it takes this map here, it takes the anisotropy, the variation function, okay, and it expands it in spherical harmonics, because this is a function on the sphere. And you look at the coefficient in that spherical harmonic decomposition. And those coefficients you can kind of one-to-one map to various parameters in the standard model of cosmology. Okay, so somehow there is a very nice understanding. So let's say like the coefficient of one term in this expansion should predict the density of baryons at an early point in our universe. Okay, and other coefficients tell you different things. Okay, so somehow let's say the understanding or one of the hopes in cosmology is to find a way to explain how these anisotropies, which are very small here, okay, then start to kind of double in on themselves and grow and grow and grow to give us the structures that we see today. Now, of course, I'm not going to be able to do that in a little maths model, but we'll see how far we can go. Okay, so my starting point in cosmology, as I've said, is that we have isotropy and homogeneity. And what this does is it simplifies a lot of the degrees of freedom in the space-time metric, okay, because it forces the space-time, that object G, to take a very specific form. So in these coordinates here, I just have minus dt squared. I just have some some cosmic time observers, and for each time they look out on their three-manifold M, okay, with some metric Gm, and these three slices are expanding at some rate given by A of t, which is called the scale factor. So you really should just think of this as, maybe you've got your universe and then it's expanding at some rate A of t. Now, I realize already I just keep saying M as if it's compact. You might say, why should M be compact? So let me do my next slide. Okay, so we also have isotropy. The isotropy, forces this three-manifold to have constant sectional curvature. Okay, because you're in 3 dimensions, there can only be 3 possibilities. And in particular, the possibilities are like hyperbolic space, R3 or S3. You can also take quotients of these spaces. Because we have a finite speed of light, there's only so much domain we could ever reach or be influenced by. Okay, so kind of without loss of generality in these models, we typically take the space to be compact. So in today's talk, in particular, I'm going to be taking T3, and I'll just mention that this is actually what the standard model of cosmology uses. Yeah, question?
So A at 0 is 0, right? And then it's increasing.
Yes, and then it's increasing, yeah. But let's say we're just going to start it at some T0, and we're going to start it later on. Okay, so this is my space-time. Right? It has this very specific form, and on the right-hand side of the Einstein equations, I have matter fields, and they also take a very specific form under this assumption of isotropy and homogeneity. So in particular, I'm not giving you all the details here, of course, but the matter, it turns out, needs to take the form of an idealized perfect fluid. Okay, so it's a matter field which is described by a function which we associate with density, a function which we associate with pressure. The particles move along have some forward velocity. Okay, so they're moving in space and time. Yes, and we'll see the equations again later on, but somehow for all intents and purposes, this is what we call an idealized perfect fluid. It's relativistic because I'm working in the context of general relativity, okay, but it does generalize kind of non-relativistic fluid dynamics, okay, compressible Euler. So because we have so much symmetry in this setting, okay, the full system of PDEs would be the Einstein relativistic Euler PDEs. That's what they would look like. But because we're now in isotropy and homogeneity, we just get ODEs. Okay, and so these ODEs actually just are the following ones here. So the first one here is kind of like a continuity equation, like you'd have in fluid dynamics, dt of the energy density, or that density, sorry, rather, and then we've got some pressure in terms on the right-hand side, and then this other equation here is Ricciarduri. Yeah, let me not say further about that. But we don't have enough equations to close the system, okay, because if I just look at here, I've got an equation for rho, an equation for the scale factor A, and these p's, this big P and this little p, are the same P, but we don't know how to solve for that capital P, okay, and so for that you need to make a choice of, like the thermodynamic properties, okay, of your fluid. And so in cosmology, the standard thing to take is just a very simple linear barotropic equation of state, okay, which means that barotropic just means that the pressure is just a function of the density rho, okay, there's no entropy, entropy is constant, and I just have some linear function, I just have some parameter here, k. Now, k, this parameter k is going to be very important for my talk, and in particular, the 2 important cases that appear in cosmology are these 2 cases here. So when this parameter k vanishes, we have no pressure, and we call this a dust fluid. Okay, so you've got your particles here. They are not exerting pressure on each other. They are only interacting through the gravitational field. Okay, the other side of that is then k is equal to 1/3. Okay, pressure is equal to 1/3 the energy density. This is called a radiation fluid. Okay, and for all intents and purposes, you should think of it as modeling the CMB radiation. Okay, that early relic radiation, we could model it by, you could obviously model it by electromagnetism and Maxwell's equations, but we could also do some approximation and model it with this radiation fluid. And again, these are kind of the constituent ingredients in the standard model of cosmology. Okay, so because of all this symmetry, I can now write down some explicit space-time solutions. Okay, some explicit solutions to the Einstein relativistic Euler PDEs. I'm going to give you 2. So the first one is called the Friedmann-Lemaitre solution. Okay, and so the things just to kind of identify for us here is that I don't have a cosmological constant. So this is going to be used in the early universe. I have a scale factor, A of t, which depends on the type of fluid. Okay, so it depends on the parameter k. Maybe it's good just to write here, just so we have it here. So P is k times rho. Okay, so the speed of expansion depends on the type of fluid. And of course, you're not creating matter for nothing. Energy is low enough at this point. And so as things expand, the energy density needs to dilute at some rate in time. Okay, things are moving out and it needs to dilute. So what's important here actually is that while this space-time is expanding, it's an example of decelerated expansion. Okay, so the second derivative here is negative. By contrast, another explicit solution is the de Sitter space-time. This is something that Claude mentioned in his talk, although with a black hole probably. And what happens now is I allow for a cosmological constant. And as you'll see, if you allow for lambda to be positive, the solution grows and expands very, very quickly. Okay, so in this case, the scale factor grows exponentially fast. Okay, and that's what we wanted to model. Let's say in our current epoch of our universe, things are moving apart very quickly. Okay, and of course the energy density needs to decay to zero. All right, and this is an example of accelerated expansion because the second derivative of A here is strictly positive. Very good. So these are solutions that are used to describe different epochs in our universe. So excuse my little picture here, but our best understanding is that after the Big Bang, okay, our universe went through this period of decelerated expansion. First of all, it was dominated by radiation fluid, okay, and that's when K is equal to 1/3, in which case the scale factor grew like T to a half. Then things started to cool, the radiation started to dilute, and at that point the dust matter took over, so that's when K is equal to 0, okay, and then the expansion started to increase slightly, went to A equals T to the 2/3. And then, as I said, we're not entirely sure what happened, but the acceleration changed, okay, and we went into a period of accelerated expansion, and we modeled this through de Sitter. Okay, so I realize it's not, unfortunately it's cosmology, right? It's very hard. You can't model it in some like neat little theory, but this is kind of the main idea is cosmologists will use these three models and try and understand gravitational perturbations and kind of matter perturbations in each of these epochs. So let me then tell you about what I am interested in. So as I said, cosmologists will look at gravitational perturbations. Sometimes those things rely on linearizations, okay, and approximations. And what we are interested in is trying to do some nonlinear PDE theory. So, of course, one thing you could do is study these solutions under the full Einstein relativistic Euler equations. Okay, I can pose this as an initial value problem. I have a distinguished solution. I could look at perturbations and see what happens. It's a very hard system of equations, okay? So we can do it in some settings, but for today, what I'm just going to do is just study the relativistic Euler part, okay? So just the fluid equations of motion. So what I've written here are these fluid equations of motion, the relativistic Euler. So we have an equation here for rho, okay, which this top equation you can view as the continuity equation. And I have here mu and mu because I'm using Einstein's summation convention. Okay, and then down here I have an equation for the pressure. This would be the continuity, the momentum equation. Okay, so these are the two equations that I'm going to study, and I'm going to fix my metric. I'm going to fix the geometry, G, to be some fixed geometry. Okay, I'm not going to let it evolve under the Einstein equations. So let me give you a little brief reminder of some of the literature. Okay, we're talking about fluids equations, so your question could be, could a shock develop or not? Okay, what kind of global dynamics can I have? So just to remind you, of course, if I'm in the setting of non-relativistic fluids, it's very canonical that smooth solutions, smooth initial data, can lead to shock singularities in finite time. Okay, so the first derivative of one of your fluid variables would go to infinity. So this is going back to work of Riemann and many works since then. So this is in the non-relativistic setting, and you say, well, what happens in the relativistic setting? Okay, in a world which is compatible with special relativity. And so the first, I guess, big result in this direction was by Christodoulou. So what he's looked at here is the relativistic Euler equations on a fixed geometry, a fixed Minkowski geometry. And I'll just write it down here, just because will be useful later on. Okay, so he fixed his metric and he could show that for a large class of initial data, it would develop a shock in finite time. So the same kind of result happens, let's say. But then there's this other work which was done by Brouwer, Rendell and Euler, which is very suggestive. It's not in full Einstein gravity, it's in a Newtonian analog, but it's very suggestive of what would happen. And what they did is they studied the kind of the relativistic Euler equation, or the Euler equations really, they weren't relativistic, but they studied these equations in the setting of fast cosmological expansion. And the intuition is just the following, is that if things are expanding very, very quickly, whereas you'd normally have your fluid flow lines kind of coming in along characteristics and intersecting, and then you get your discontinuity, now your space-time's moving apart, right? So those things just can't intersect because they're moving apart. That's all the intuition is. Okay, so in this setting here, they had lambda to be positive, they had fast cosmological expansion. Okay, and what it does in the PDEs is it gives you lots of kind of what I might think of as friction terms, damping terms rather, okay, which kind of leads to global existence and you don't get shock formation. Okay, so this is a very brief literature. So let me now tell you the setting for our problem. Okay, as I said, we're looking at the Euler equations and we're going to look in the setting where my scale factor is a polynomial rate. Okay, so just to have it written there. So this is called a power law spacetime. It's actually something that is very much used in cosmology. It's not kind of pulled out of thin air. You will notice that when alpha is equal to 0, okay, I kind of get the Minkowski spacetime. Right? So Minkowski is like some degenerate solution in that case. So this power law spacetime here, it includes the class of spacetimes that are used in these fundamental models in cosmology, okay, where the scale factor is like t to the 2 over 3, 1 plus k, and all this kind of stuff. So it includes that. But alpha is going to be this free parameter that we're going to use. So what I would like to do is I'd like to fill in a phase space or a picture as follows, where on my x-axis, I'd like to have the expansion rate. Okay, I'd like to know how quick my cosmological spacetime is expanding, right? And I'm expecting to get a blue regime there of decelerated expansion, okay, and then a purple regime of accelerated expansion. So A double dot negative, A double dot positive. Okay, those are the things that I think are going to determine or distinguish the behavior of my fluid. So that's what I'd like to have on my x-axis, and on my y-axis, I'd like to have a measure. So I say here the fluid speed of sound, and I didn't actually write that on the slide, sorry, but just to say that you can also identify this parameter k here as the square of the speed of the sound waves. Okay, it's another way to view it. Okay, and in cosmology, as I said, people are very interested in dust and they're very interested in radiation, and of course these things can't be exact, so we'd like to be interested in the regime in between as well. Okay, so this is what I'd like to fill in. So as I said, alpha is going to measure the expansion rate. The scale factor is like t to the alpha. Alpha measures how quick this expands. I'm going to have decelerated when alpha is less than 1, and accelerated when alpha is bigger than 1. Okay, and then on the y-axis, I interpolate. I can go from dust up to radiation. Okay, so what is the intuition that you should have here? Is the following idea that, what I've written down here. So if k is small, that means the pressure is small. If I don't have much pressure and things are moving far apart quite quickly, alpha is big, I would not expect shocks to form, okay, which I'm going to denote by green. On the contrast, if I have quite a lot of pressure, k is a larger number, and let's say alpha is not so big, it's not pulling apart as quickly, I might expect shocks to form. Okay, and that's what I'm going to denote by red. That's the intuition that you might have. So let me now tell you some of the results in this direction. So I wonder if I've got it. Yeah, so what I've drawn here is kind of some of the previous work that was done. So just to unpack this a bit, so I mentioned this work of Christodoulou that shows shock formation on a fixed Minkowski background. So remember, Minkowski is this degenerate cosmological model when alpha is 0. So we can kind of think that along this line, the fluid will always be developing shocks. Okay, then there was some other work by Jared Speck along this top line here, which you'll see here kind of agrees with this intuition. Okay, when k is large and alpha is small, which is what we've got going along this top line here, we do get shocks developing. But then what was noticed and what was studied, maybe let me see here, this star, whole bunch of works, was that in the regime of accelerated expansion, okay, which is this region here that I'm kind of circling with my mouse, shocks do not develop. Okay, the fluid always stabilizes. Okay, so people here could even look in the setting of Einstein-Euler. So you could even put in the Einstein equations here, okay, and look at the fully coupled problem. Okay, and then we also have this result on the bottom here, which maybe is good to just analyze in this top intuition line here. So here, we're in the case of dust. Okay, so K is 0. So we have K is small, it's 0, can't get any smaller than that. And we see that actually, in fact, no shocks develop, and we can go all the way down to alpha is equal to 1/2 plus a little bit. Okay, but I hope you see that, we don't really know we didn't know anything that was happening in the middle, right? And that's what I've been interested in with my collaborators. I'll just first mention that before you go into this middle region, you need to worry about the line where alpha is equal to 1, okay, what we call linear expansion. And while it might not look it, it took a while to prove that these things were stable. That's what I did in my postdoc. And these, things were a little bit hard, but we can also study the full Einstein-Euler equations. But the thing I wanted to tell you about today is our results from these 2 recent results here, which is where we're able to look in this interior box here, which is the setting of decelerated expansion. So let me remind you that this is this early epoch, okay, early epoch in our universe. So what we found is a transition line, which I've denoted here by this black dotted line, which is quantitative, okay, it has a specific formula. And what we could find is that on one side of this dotted line, okay, in this region here in green, we could prove analytically, okay, that shocks do not develop. Depending on the kind of initial data that I set. I should say with all of this, qualifying all of this, that you could probably set up initial data in some funky way, put things focusing or something, and you'd be able to develop shocks, okay? But for a certain open class of initial data, we don't get shocks developing here. Then on the complement of this line, okay, in this red, what I've denoted here, in this red region, we were able to solve our equations numerically. Okay, and for all intents, for what we see, or what we really believe is happening, is that the fluid is developing a shock in finite time. We're getting some kind of density gradient blow up, okay, which is telling us that we're getting, naively, let's say, a first step towards some kind of structure formation. But of course, there's a lot more that you'd have to do to get to that point. The other thing to note on this line, I've drawn in brown here. Okay, so the brown line here denotes the actual solutions to the Einstein-Euler equations, the Friedmann-Lemaitre solutions. Okay, so these are the ones that are used in these main models in cosmology. Okay, and you'll note that they all lie along in this unstable region. Okay, that is not so surprising, but I think what's quite important is that we are kind of, as we'll see when I get to the equations, we are seeing shocks coming from Burgers-like terms. Okay, so our shocks are going to come from Burgers-like terms, whereas in cosmology they tend to work in they do linearized arguments, and so these Burgers, these kind of UUT or UUX terms, these things like that, they throw them away because they're higher order. Okay, so they're kind of it's like quite a different thing in terms of what you call a shock. The other thing which I think is quite interesting to note, okay, maybe it's a bit technical, but what we see here is that the behavior of dust does not approximate the behavior of fluids with a non-vanishing speed of sound. And so in particular, if you come down your line here, for example, and if you come down from here, my mouse is showing, if you come down here, you might have, some behavior, your dust, it looks like it's unstable, and then it flips into something that's stable. And this is quite important, I think, because in cosmology, lots of times they will use dust as some kind of model matter, but I think it's not well understood how good an approximation that is. Okay, maybe setting the pressure to be 0 is too strong a restriction. Okay, so let me tell you a little bit about the proof, and I'll just say, obviously, just a couple of words about it. So this is the theorem in the analytic setting. Okay, so all I'm saying here is that if you're to the right of that transition line and you take small initial data in some Sobolev space, then your emanating solution to the relativistic Euler equations will exist globally and decay at a certain rate. Okay, and I introduce in here a bar notation, which is to denote the average. So I told you that I was working on T3. In our first paper, we worked in a T2 symmetry class, so that's why here I'm just averaging over 1 torus. But in the later paper, we could remove that symmetry restriction. Okay, so we can do things without that symmetry restrictions. In the analytic setting, of course, in the numerical setting, we have that symmetry restriction, so we can do numerics just on a 1+1 system. It's a lot easier to do. Okay, so let me give you just a couple of comments on the proof. So broadly speaking, in these kinds of cosmological problems, the mechanism for decay looks like something here represented by this equation for phi, where you might have dt of phi is equal to minus some positive number over t times phi. Okay, because when I Gronwall that up, I get that phi decays like t to the minus positive, which is good. And then, of course, what kind of shock mechanism do you often have in fluids equations is you have the Burger's equation here, nonlinear Burger's, so we have dt psi plus psi dx psi. Okay, and as I said, these are kind of important quadratic nonlinearities that in fluid dynamics are the things that drive our shocks. And what we get in this setting is we get a competition between the two. Okay, so we have some kind of competition between these two effects. So what I'm going to write next is you need to kind of normalize your variables because things are expanding with the space-time, so you do some kind of normalization. And so what my fundamental variables now are going to be v for the fluid velocity and L for its energy density. Okay, and I'm just writing the equations in T2 symmetry because you get the gist. Okay, so we get the following equation here. Equations here. So let me unpack a little. So the first equation is dt of our velocity variable. And what do we get here? We get minus some coefficient alpha 1 minus 3k divided by t of v. So this is something that would drive decay. And as you'll see, the rate of decay depends on alpha, the rate of expansion, and it also depends on k, the type of fluid. Okay, it depends on that pressure parameter k. But then competing against this decaying term, we have the Burger's term here, we have v dx v, all right, but it is diluted by some parameter 1 over t to the alpha. Okay, it's dampened by the spatial expansion. And that's probably the main place to see the competition. Of course, we also get competition in other terms, but I think this is kind of the really kind of driving point to see the competition between these two dynamics. Okay, so what I have shown here, okay, is just a picture of the numerical shock detection. Okay, so just to show that on one side of our transition line, we really do think everything seems to be blowing up, and you work at decreasing your amplitude of your solution, and the rate of blow up will shift, but you can quantify it, the time of blow up rather, and so this we believe is giving some polynomial rate of blow up. Along the transition line, the numerics indicate that the blow up time or the breaking time occurs at like exponential of 1 over epsilon, where epsilon is the size of the initial data. Okay, so you have this transition along that line. And then on the other side, the numerics, nothing blows up, things seem to exist globally. Okay, so kind of the numerics here are a very nice complement to the analysis that we can do in this smaller region over here. Okay, so I only have a couple of minutes, probably 3 minutes left. So let me just very briefly say a couple of words on the proof. We'll see how far I go, okay? So the first thing that we do is we try and derive some decay from the problem, okay? And we use the compactness that we have here in the spatial component, okay? The fact that they're working on a torus. And so in particular, if I just jump back to this equation, okay, so this is my velocity equation, and I have something which is good, and I had my advection term v dx v, which is not great. But if I integrate this over the torus, then this is going to integrate by parts, flip around, this will become a total derivative. Okay, so in particular, when I'm looking at the average velocity, okay, by integration by parts, it obeys quite a good estimate, okay, where I get dt of v bar, this average part, this good term here, plus, obviously it's very important what kind, the degree and the type of polynomial that you have here, okay, but it's something that can be controlled. Then combined with this, we work with an energy argument, so we control the solution by a bootstrap argument, and so we have an L2 energy of derivatives, which basically means we have a dx of v and a dx of L term that you need to control, okay? And of course, you just need to pick your coefficients in right ways so that you enable a cancellation of your top order terms that we have, okay? So there's not too much going on there that isn't seen before. So if you do this naively, okay, you will get the following energy inequality, which says that the evolution of the energy is like minus. We've got some good coefficient here. But the thing that we get back, Okay, integrated on this torus is just dx of v, which is just the first part of the energy. So we don't recover the full energy. Okay, it's not coercive over the full energy because we're missing the dl part. Okay, and so the key idea is to actually obtain this extra decay-inducing term by adding a correction to the energy. Okay, so you add a correction term which you can show for small data. It's going to be the other terms are coercive over it. And when you do that, when you take the time derivative of your corrected energy, it's a balancing argument where you're going to pick up a term with a good sign. I think it's this one is probably, or maybe this, no, sorry, you pick up a term here with a good sign. So that's great because that gives you back your dxl term, which we were missing. But then you pick up a term with a bad sign, okay, which works against the good decay that we had from before. Okay, so you just need to pick one of your parameters to maximize the decay in this argument. Okay, so that's what we do. You pick this delta here so that these two coefficients are equal to maximize the decay, right? And then that then gives you the following evolution for your corrected energy, where now the time derivative of that corrected energy returns here on the right-hand side. You get the full energy functional. You don't miss part of it. You've got the full thing here with this good factor at the front. So then what remains to be done is to understand this higher order term, okay, these higher order terms that we get here, okay, and it's exactly in this argument where you kind of, I'm really running out of time, you really put in your bootstrap assumptions, and at some point there, what will pop out is the critical exponent. And basically, in order to close your bootstrap argument, you get this critical exponent. It's come from the kinds of nonlinearities that you have. And in order to have this thing kind of being something that doesn't dominate, that actually you can control, we need to take this critical exponent so that k is less than k crit. Okay, and so that's where it pops out from. Okay, so that is all I had to say. So I hope at least you've learned a little bit. Okay, we find this new stable and unstable behavior for perfect fluids in decelerated cosmologies. We'd very much like to understand lots of things, in particular the unstable regimes. We'd like to understand it better, but there are also a lot of other dissipative effects that people use in cosmology, and it would be nice to understand those as well in the future. So thank you very much for your attention.
Thank you very much for the nice talk. So the picture you had with the red and with the green part, the conjectured.
Yeah.
So really, the green means small data doesn't develop shocks. Mm-hmm. So in principle, you could construct large data that does develop. Okay.
Absolutely.
So and red means that there is arbitrarily small data that leads to shock. Not necessarily every small.
Exactly,
data.
not necessarily every, and I think you could set your data so that it like shoots out. You get a bit of a velocity push, and then maybe it wouldn't develop a shock. Yeah.
Okay, thank you. So this k, you assume that it's smaller than 1/3. I guess it comes from this energy estimate, right? If it's greater than 1/3.
Yes, it's a very good point. Yeah. So when you go above 1/3, the stability properties change quite significantly. Really, in cosmology, they typically just look when k is less than or equal to 1/3. So they're not looking in this superradiative case. Yeah.
Okay, so just one more question. So you took the linear barotropic equation, but in fluids, often people consider nonlinear barotropic equation of state. Is there any conjecture in this?
No, but it's certainly something to look at. Yeah. So you can look at polytropic equations of state as well. That's more done in astrophysics, which is a slightly different setting to what's done here, but it's certainly something that you could do. And I think actually, I'm pretty sure Max, who's now my postdoc, I think he had started to look at that. Actually, one thing you can also do is you can look at this. So here I'm on T3. You can look at it on other geometries, so like sphere and hyperbolic space and things like this. And actually then the line does shift in one of the cases. Yeah, so yeah, you can also shift it slightly with the curvature too.
Okay, thank you.
Yeah.
You had mentioned that you had these separate proofs for T1 versus T3. I was wondering if you could comment on, do you somehow reduce the T3 case back to T1?
Oh yeah, sorry, it's very similar in the proof. the proof going from T1 to T3 is very similar. Luckily, I mean, there are some, you need to be smart, kind of writing the curl in a particular form to split some vorticity in a certain way. But for all intents and purposes, that's not so much the challenge. Certainly, the numerics is what is challenging, and that's why the numerics need to be in T1.
Mm-hmm.
Yeah.
Okay. Thank you.